Welcome everyone, and sorry for the inconvenience. So YouTube today is down. The broadcasting part of YouTube is down. We can't use it. So now we're reverting to Zoom. I hope it's not too much of an inconvenience for all of you. In any case, welcome to the MIT Category Seminar. So this week, we have Jaz Myers from the Johns Hopkins University. He's gonna talk about one of the links between category theory and homotopy type theory, maybe a more unconventional one. So here we're using homotopy type theory to do category theory, almost basing category theory to homotopy type theory. This is particularly interesting if you look at notions of uniqueness and uniqueness up to all isomorphisms and all these notions of uniqueness you get, for example, when you see universal property. So I'll just give the word to David. If you can, please still ask your questions on the Zulip chat so that it will stay there, and so people who cannot connect right now will still see them and see the answers, okay? But okay, David, you're welcome, and please, welcome to speak.
Thanks, Paulo. So yeah, thanks for joining me here, despite the technical difficulties and the general state of affairs. I hope you and your loved ones are safe and doing well. So I'm going to tell you what I hope is a nice, entertaining story about homotopy type theory and how you can use it to do category theory. The story I want to tell is that homotopy type theory is a new foundations of mathematics. I'll go into exactly how it works. And it's a natural foundation of mathematics. It's a foundation that feels really close to home, the way that you do mathematics, the way that a lot of us do mathematics, especially if you're a category theorist. So I'm going to try and highlight how doing math in homotopy type theory feels in some ways a lot like doing math in category theory, and also how doing category theory in homotopy type theory allows you to avoid some of these little, niggling doubts you might have, or like little very technical, very annoying problems with regards to choosing objects that are only defined up to isomorphism. So in homotopy type theory, it will turn out that that's fine. If you only have an object defined up to isomorphism uniquely, that's a perfectly good definition of that actual object. You don't need to invoke a choice principle. You don't need to do some fiddling around. You don't need to construct some kind of opaque structure and then never refer to it again. The proof is in the pudding. When you've proven that you have a unique thing defined up to isomorphism, you actually have it. So in order to make that feel real, I'm going to go through an introduction to homotopy type theory. I haven't had a really good chance to try and time this talk very well, so I may have to skip ahead. The slides will be up on my website later if you want to go and see something if I end up skipping it. All right, so let's start. Homotopy type theory. It's a new kind of foundation of mathematics, and it starts with this question. How do you identify one mathematical object with another? Well, it depends on what type of thing they are. So, for example, to identify the affine plane with R2, we need to choose a point to serve as the origin. And that lets us identify everything relative to that point. To identify the tangent space of the two-sphere at some particular point with R2 again, we need to give a basis of it. And when we give this basis of it, we can identify any tangent vector written in this following way with this given column vector. Now, to identify HN/Sn, the nth cohomology of the n-sphere, valued in the integers, with the integers, we have to choose an orientation for the n-sphere. And more prosaically, but no less interestingly, to identify the natural number n, such that the fourth homotopy group of the three-sphere is isomorphic to Z mod n with the number 2, we just need to prove that n equals 2. And so this may seem like a really weird way to phrase that last question, right? We have a number n, which is the number that is the number n such that z mod n, that 4s3 is isomorphic to z mod n, and we want to show that it is too. Right? This is actually how this proof goes in homotopy type theory, so it's a nice way to think about it. So we have all these different ways to identify mathematical objects, and you can think of your favorite mathematical object, and I'm sure you know how to identify it with another thing. Especially, the idea is usually you have some big construction, you have some part of it, and that is, maybe it's coming up in your work, but then you have this fixed object that we all use, and we've all built a lot of tools for studying, say like R2, compared with the tangent space at this particular in S2. There's a lot of tangent spaces on S2, right? But they're all isomorphic to R2, and R2 is where we do all of our work, where we have all of our theorems. I mean, ultimately, we express them specifically about R2. So a lot of mathematics is just identifying your particular situation, which is standard reference situation, and then transporting your results back and forth between these two situations. So in homotopy type theory, we take this as a basic notion. And what it turns out is that we can give a very simple but uniform definition of identification in mathematics, which is not trivial. So type theory is a foundation of mathematics from scratch. So a type is a type of mathematical thing. And type theory gives rules for making new types and new terms of them. So term is the type theory word for like element. So for example, and this is notation, we use a colon to say is a type of. So we have a term, colon, its type. So for example, 3 is a natural number. And the natural numbers are a set. And the tangent space of a manifold M at a point P is a real vector space. And the real vector spaces are a type. So in general, every type is of type. And if you ask me what type does type have, it's some boring thing where we have to have universe levels to avoid paradox. But I'm not going to care about that. And, people and I have cared about it, so I don't have to. Okay. So I want to make something very clear about what it means to be of a type. This is what it's called in the type theoretical literature, a judgment. It's not a proposition that A has type capital A. It's not up for debate. It's what it means to be that thing. So to say that 3 is a natural number is a judgment about what we mean by 3. It's just the part of the fact of what 3 is that it's a number. And similarly, there are different 3s in our normal mathematical practice, right? You have the 3 that's an integer, and you have the 3 that's a rational, you have the 3 that's a natural number. And these are different. And you can tell they're different because they actually satisfy different properties. Like, for example, the second 3 is a unit. The 3 that's a rational, it's a unit, but the first one isn't. Right? Now, of course, they're all related because there are these canonical inclusions of n into z into q, and you can say that the image of 3, the integer, in q, the rationals, is equal to 3, the rational, right? Much like you would do in category theory, where you take every sub-object as a morphism, so you actually represent the function. And we use 3 equals, or equiv, \equiv, to say that a term is judged to be equal to some other term, by definition. So this is literally equal. They can be substituted anywhere. So for example, 3 is the successor of the successor of the successor of 0. We'll come back to what that is when we define natural numbers. And excuse me. So now we come to identifications. This is the big deal in type theory. For any 2 terms of the same type, we have a type of identifications between them, and we use the equal sign. Here I've subscripted it with the type they're in. You don't always have to do that if it's clear from context. And I'll actually define this in a few slides, but let me tell you how this actually works out. So for example, if V and W are vector spaces, real vector spaces, then the type of identifications between them is the type of R-linear isomorphisms between them. If X and Y are sets, then the type of identifications between them is the type of bijections between them. If M and N are smooth manifolds, then the type of identifications between them are the diffeomorphisms between them. And if N and M are numbers, then the type of identifications between them has an element if and only if they're equal. There's at most one way to identify two natural numbers. I just want to take a moment and focus in on this last property. This is a crucial property of some types, that it has at most one element. And we'll call these types propositions. We'll come back to this later. But what we see here is that being equal is a proposition. Identifying, not necessarily a proposition. There are many ways to identify two objects, and it can make a difference in your calculation how you do that. But if two things are equal, they're just equal. And we see that here. For the natural numbers, there's not many different ways to identify two natural numbers. They're either equal or they're not equal. Now, all of these are actually theorems, and they follow from the single axiom of homotopy type theory, and that axiom is univalence. So, univalence axiom states that it fixes one of these, and all of the others come from it, and what it fixes is what it means to identify types. So, univalence says to identify two types, we give an equivalence between them. I'll define an equivalence later. So, in type theory, every type has to be annotated, every term has to be annotated with its type. So you can't just have A, you have to have A of a given type. So to define functions, it's very easy. You just assume you have something in your domain, and then you write down something in the codomain. And I should mention that types are allowed to depend on terms. So for example, the tangent space at a point in a manifold is a type of thing, it's a type of these vectors, that depends on that point. So it has this free variable, which is P. And we can have a dependent function type, as they're called, or functions here, which is written A of type A goes to B of A, and they take an element of A and land in B of that element. So to give a function, we just say what it does on a generic element of its domain. So, here it is. So for example, we have this function that takes our tangent space here, because if we have a point of our manifold, we can write down the definition of the tangent space and prove it's a vector space, and therefore we get this map. And also, we can have this dependent function, so for any point on our manifold, we have the zero vector. So we get this function P maps to 0, which is a zero section, so it's a vector field. And you can see that these dependent functions, even though they might not be familiar to you immediately, are actually quite common in mathematics. We'll be using them a lot, but they're things that are very common and very intuitive. So a dependent function is just a function whose domain depends on the particular, whose codomain depends on the particular value it's taking at that time. So we can also form pairs. So if we have a type and another type which depends on it, then we can form the type of pairs. And its elements are pairs, and the type of the second element in the pair depends on the first element. So for example, if we apply this to the function from a manifold to vector spaces that takes the tangent space at a point, we get the total space of the tangent bubble. And in general, the space of dependent functions is the sections to the projection, the first projection off of pairs. Okay, so I'm now going to tell you about I'm going to define for you what it means to identify things. So I told you we have all these ways of identifying, it's this uniform definition. I'm going to tell you what that is. Before I do that, I'm going to tell you what an inductive type is. The reason is that identifications are given as an inductive type, but it's a little weird. It's a little not like you're used to. So we're going to take a stepping stone, and that stepping stone is the natural numbers, because I assume we're all familiar with the natural numbers. So an inductive type is a type that whenever we have a free variable of it, we're allowed to assume it's of a prescribed form. So for example, the natural numbers are defined by this property. A natural number is either 0 or it's the successor of another natural number. And to define a function out of the natural numbers, so here is a function, it's defined curried. What curried means is it's a function that yields a function. So this is the same as a binary function. And so to define this function, plus, we can assume we have a free variable, and we then seek an element of the codomain. So this is how we define functions. We assume we have an element of the domain, we just seek an element of the codomain. So we need a function of type n to n. So if n is 0, then we'll take this function to be the identity. And if n is the successor of something, we'll take this function to be the function that sends x to the successor of x plus m, the thing inside the successor. And in total, we get this function, this analysis by cases, and that defines plus. So the reason I did that is because we can define identifications in a similar way. So for any two terms, we have a type of identifications, and we may assume that the free variable b, the second one, and the identification p, when they're free variables, are of the form reflexivity, or refl. So here's an example of how that works. We're going to define the symmetry operation. Symmetry says that if A, that takes an identification of A with B and yields an identification of B with A, it should be the inverse, right? And so how are we going to do that? Well, it's a function. So we can assume everything in the domain are free variables, and we're going to try to build an element of the codomain. But now we have B and P as free variables. So by induction, we're allowed to assume that B was actually A and that P was actually reflexivity. But then we're seeking a term of type A is identified with A because B was assumed to be A. And so reflexivity works for that. So we get this weird analysis by cases, which you can see here. A, B, and P maps to reflexivity if P is reflexivity. So it seems like you couldn't really do anything with this, right? Because after all, you'll only get a result when you plug in reflexivity. And that's true. But you can prove identifications, you can construct identifications between identifications. So even though you're only getting a specific result when you apply such a function to reflexivity, you can still calculate with identifications. And univalence says that when you calculate with identifications, you're calculating with equivalences of types. So this is a really powerful idea. So I want to show you a bit of how this works. So I'll stop now for a few questions before I go on. Maybe Paolo could tell me if
Yeah, so there is, first of all, a question.
Yes.
So the question says, does the expression, so dependent product over A in A, B of A,
Yes.
assume that A has elements?
No. So we don't really think of a type as a collection of elements. So it might be true that some types it's impossible to give a term for them. In fact, we assume one by default, which is we assume a type that's the type of nothing. So you can't give a term of that type. There's no thing that is of that type. But in general, we don't think of them as having elements. We think of them as types of things. So it's rather immaterial whether or not it has elements or how many it has or how they're arranged. That all comes out from just its definition. And one of the beautiful things about type theory is that everything just follows from the form of the types. So no, we don't make definitions on the types. It's good for every type.
And so maybe the question could also be phrased, a bit differently as, what happens if A is not inhabited? What do we get? I guess we need something like a statement that's similar to the empty product is a one element set. Is there an equivalent in type theory?
So the empty type can be defined inductively as well. It's inductive with you can assume every free variable is nothing. So it's inductive with no constructors, in other words. And what that means is you can always define a function out of it, because to define a function out of it, you take a free variable, you have nothing, that's your result. It's sort of a ad absurdum argument. Or ex falso quodlibet, right? You you get anything from nothing. From absurdity having nothing. So from that you can show that functions of nothing are a single thing of point, and the point is inductively generated by having a single point. You can assume every free variable of it is equal to star.
Sorry, can you repeat the last sentence? I think we got a connection glitch. Functions out of nothing?
Functions out of nothing are provably equivalent to a star. So you can identify functions from nothing to anything, including dependent with star, the single point. And the single point is inductively generated by assuming the free variable is just it's a single element.
I see. So functions out of nothing are provably equivalent to star. Okay, I think that would answer the question.
So just like functions out of the empty set are provably equivalent to one element set. It's a similar thing.
Yeah, thank you. I think that answers the question. I hope so. Does that answer the question? So who was asking Mike Stay?
If I can see why you would prefer the functional version. So for example, if A is something like a vector space, there's only one element of a vector space in the sense of a morphism from the terminal object into the space. But it has lots of elements in the sense of the underlying set of the vector space has lots of elements. So just using that as an index on the product was throwing me for a loop. There's also the question of the collection of witnesses of that type, the constructible element, the constructible terms of that type, I suppose, should form a set.
That's a meta-theoretic statement, right? So that's something like saying that if we have a meta-theoretic set theory, then we can form all the constructions, but that's meta. So if you're working in the foundations, you won't have that. Like for example, the set of definable sets forms a set, not like a set in the way. Right? Like you can have your set of every expression you can write down, but that's not a set in the linguistic expression we're describing.
Okay.
And so I encourage you not to think of types as sets of collections, as collections. They're not collections, they're types. What kind of thing is it? So being a vector space is a kind of mathematical thing. Being a real number is a kind of mathematical thing, right? Now, are there many different real numbers? Yes. But it's not the way we think about it in type theory to say that that the type R is all the real numbers. No, the type R is what it means to be a real number. And
so then how should I think of a statement like A cross B is the type of pairs little a, little b, where A colon A and B colon B?
Well, good question. That's a good question. So if I go back here, what this means is from any term of A and B, I can get an element of A and an element of B. From any two elements.
What does element of?
I'm sorry, term of. Term of A and term of B, right? So from a term of type A of type A cross BA, I get its first projection, which is of type A. I get its second projection, which is of type B. From any A and from a B of type B of A, I get a pair of the given type. And these are judgmentally inverse. So when I take the pair based on first and second of a given term, I get that exact term back. Like those. I'm judging they're judged to be the same, not identified, they're judged. And similarly, if I take, Eric comma B and take its first half projection, I get A, its second projection, and then you can. Does that make sense? and only one of those has to be checked.
Certainly the projections as things saying, I mean, in category theory, we often have categories that are not sets equipped with structure. And in as much as morphisms make sense there, the projection morphisms make sense here. It's just the language, A colon A and B colon B of A. The assertion that a term is of a particular type, it's not clear to me how you can have terms as elements. I mean,
So Emily Real has partially answered your question, actually.
I'm going to have to move on at this point.
Yeah,
but
go ahead.
I want you to think about A colon A to be a mathematical object, little a, which the kind of thing it is big A. Right? And so the pair A comma B, the kind of thing it is a pair. And if you just think about that in that intuitive way and don't try and do the categorical semantics, I'm not going to talk about that in this talk. And you can, maybe we can go to the julep afterwards and talk about it. But more confusing than just taking it at its face value. That you have mathematical entities, you know, like 3 is a number, pi is a real number. You know, this given vector is a vector, this given space is a manifold, and so on. And thinking of that in that way, it'll be much easier. Okay.
So Emily has actually partially answered your question. It's on the Zulip if you want to check. Thank you.
Yes, I will read that. Thanks. Just one last thing. Could you move the mouse pointer off the middle of the slide?
Sure. Is that better? I can't actually see the mouse pointer.
Maybe it's someone else's mouse pointer, but it's still there. Oh well.
This doesn't move it? Okay. I'm gonna keep going. Is that all right?
Please
okay.
go, yeah.
So I want to show you a little bit of what it's like to use these identifications in this way. So first of all, we have transitivity identification. So in other words, we can compose identifications. And the way we do this, and all of the things in the next few slides, is just going to be by a quick induction. So suppose we have an identification of A with B and an identification of B with C. We're going to get an identification of A with C. How do we do it? Well, these are all free variables right now, right? So Q is a free variable and C is a free variable. And because of that, by induction, we're allowed to assume that C is judgmentally B, is equal to B, and Q is equal to reflexivity. But in that case, what we're looking for is something of type A is identified with B. And we already have something of that form. We have P. So we can define this in that way by induction. We take Q to be refl, and then we define P dot Q to be P. And that gives us this in general. So we can define a inverse. So by that, it actually means that this is exactly, if we do P dot refl, it's exactly P by definition. But we can also do the other side. And again, this is by a little induction. And similarly, we can do associativity. So for associativity, what you can do here is see that if we take R to be refl, this will be exactly P dot Q is identified with P dot Q. And because of that, we can take refl. So that's our induction. So if it sounds like it's a little easy, that's because it is. It's something surprising about the way this gets going, is that you get a lot for very little. But there's a trick to it. It keeps growing. So an interesting, a really nice fact about this is you can keep going. You can get as many coherences as you want. So you want to show that these associators satisfy the pentagon axioms, you can, and so on. And again, it's been proven through a lot of hard work of a lot of people that this in fact reproduces homotopy theory. So you really do get all the correct coherences of all levels. But again, I'm not going to talk about that in this talk. Now, in homotopy type theory, every function is a functor with regards to identifications. So given any function, and supposing we have some identification between two elements in its domain, then we get an identification between their images. The way we do it, again, is by induction. So if P was REFL, then we're looking for something of type FA1 is identified with FA1. Well, we can take REFL. And so we get this F lower star, that's the push forward of our identifications. And we can show that this is a functor, namely we can give this specific identification here, and we can show it has coherences, so it pushes forward the associativity to the associativity in the right way, and so on and so on. And in general, all these lemmas end up being you write down what you want, and then it's true, because if this thing was reflexivity, it would be reflexivity. So what's really interesting about this is the way it feels to prove this. It's in some sense it's similar to doing category theory on this deep level, which is that in a lot of times the problem is you're working in some specific place. You want to give some specific identification between some specific complicated thing that's really what you're working with. And what you have to do is ask the right question. What would this look like abstractly? And once you've asked the right question, the proof is trivial. And so in that sort of deep sense, the way it feels to do homotopy type theory is a lot like the way it feels to do category theory. The hard part is asking the question. The proof flows. So we can calculate also what it means to identify functions in pairs. And from this, we can build up identifications in all our complex types. So given two functions, then an identification between them is the same thing as a function that takes an element of the domain to an identification between the images. So this is like function extensionality. And I will note that this one actually uses univalence in a non-trivial way. It's not just an application of induction. So this is a theorem. Also, if we have pairs, then we can identify them with a pair of identifications. But now there's a little twist. So we have an identification of the first element in the pair, but the thing is the second elements are not in the same type. So B1 is in capital B of A1, and B2 is in capital B of A2. So they're not of the same type. We can't compare them for identification. We can't identify things that are of different types. But we know that A1 is that we have an identification of A1 with A2, right? So that should mean we should be able to produce an identification of BA1 with BA2, whatever it is. And we get this from univalence. So we can apply B as a function from A to type. So we can apply that to P in the way I did on the last slide. So I'll go back really quickly. If you see here, that F lower star, that's the same as that B lower star. But now, because of univalence, this thing, which is an identification between capital BA1 and capital BA2, it's actually an equivalence between these types. So we can apply it to elements, to terms. Excuse me. So we can apply it to B1, and then we can see that that is identified with B2. So we see that an identification of pairs is a pair of identifications, but where we push forward the second element in the pair, second term in the pair, to along the first identification. Okay. So I want to give you a taste of what it's like to actually calculate with this. So the basic idea here is that the identifications between mathematical objects, if you remember that early slide, it's what you expect it to be. You can prove it. In fact, a good definition of the obvious identifications is just the one that you can prove from, or a one that you can prove in homotopy type theory. So as a taste of this, let's see how you can calculate what it means to identify two magmas. So a magma is this ultimate precursor to a group. It's just a type of a binary operation. Okay. So I'm going to denote the type family or the dependent type of binary operations in a given type by and that will help me with notation. So let's see the type of identifications between two of these magmas. We're going to use that pair typing. This is a pair of identifications. So we have an identification between their carriers and this push forward identification. Right? Okay, so now it seems like we're a little stuck. Like, what the hell is binop star E? Well, we can take a guess, right? What would we want it to be? Well, we would want it to be conjugation, right? And so to see if this works, right, we just write down that type we're looking for, that this is an identification of binop star E with conjugation by E. And then we're just going to prove it. And how do we prove it? Well, if E is a free variable, we can use induction. So if E was refl, then binop star E is refl, is reflexivity, and so is conjugating by the identity, right? Conjugating by the identity doesn't change anything. So reflexivity is our witness. And so therefore we can make this calculation. We see that it's the same thing as saying that for any two elements of B2 terms, I'm going to say elements because I can't stop it apparently. But I mean term, it's just things of that type. We can see, this is using function terminology first. And then we can take that binop star E and turn it into conjugation. And now what we can do is do a little twiddle. We can take that E, move it to the other side, just like we're used to. And that's just like there's a bunch of series of lemmas you would use to do that. And this is not exactly what we maybe would want, but it's okay. Like E is an equivalence, right? By univalence, E is an identification between types. It's an equivalence. So we can do a little twiddling and see finally that it looks like this. And so this is how you do a calculation of identity type. And there are a lot of general theorems. So there's a very nice theorem in Homotopy Type Theory that gives a notion of when you can just say an identification between two things is given by an isomorphism in a particular category. We'll come back to that. Okay. So this is just a quick slide to tell you what an equivalence is. I'll mention it because I need the notion of contractibility, but I'm not going to actually go into univalence and how it works in particular. I'm just going to assume it invisibly this whole time. It makes everything tick. So the fiber of a function over a particular element term of its codomain is the type of pairs consisting of an element of the domain and an identification of its image with that chosen element. And then a center of contraction for a type is an element of it, so that every other element has an identification with it. And that's an English phrase. And how we turn that into a type is as follows. It would be a pair consisting of an element and a function that takes any element and gives you an identification with your chosen element. And so now a map is an equivalence if its fibers are contractible. In the same way, we take a function, being an equivalence, the type of F is an equivalence, what you might say is witnesses to this, takes a given, the type of that Y should be B. Take a element of the codomain and show that its fiber is contractible. Okay. So there's a really special feature about this, and this is Blavatsky's sort of great contribution here is noticing that you can express this notion of contractibility and that it has this property and the rest of this theory that sort of starts to build there. This is where really the germ of the whole theory is that if you have any two centers of contraction, there's a center of contraction of the type of identifications. So for any two centers of contraction, the type of identifications between them is contractible. And of course, then it stacks. That other thing is contractible. So any two proofs of that are themselves identifiable. Have a specific identification, and so on and so on. So this is a really useful property. So you remember when I said there's at most one way to identify two natural numbers. Well, this is very similar, right? There's at most one way to give a center of contraction for a type. And so we single out these kinds of types. We call them propositions. So a proposition is a type with at most one term in the sense of identification. And it doesn't mean just that it is possible to identify, that there is one term and everything is identifiable with it. No, it means that for any term, you have explicitly an identification with a given term. So a proposition is when the type of identifications is contractible for any two terms. So for example, for the natural numbers, if you have two numbers and they're equal, then the type of identifications between them is contractible by reflexivity, and everything's just the same as reflexivity. And that's actually approved by induction. It's a fun exercise. If they're not equal, then it's empty. There's that by ex falso quod libet, anything you want is true about those identification types, in particular that are contractible. So now we can build up. So remember, equality it feels more like a proposition, and that's why I've been using this word identification for what I've been writing with the equal sign. Here I've been using as identification in general, but often it means equals, and equals is a proposition. And we can actually single out a class of types where you can identifying things is a proposition. Being identified is a proposition, and we call those things sets. So this is how we define a set as a particular kind of type. And we can keep going, because now we can take a type that, for any two elements, there's a set of ways to identify them. And this is a groupoid. So for example, the type of all sets is a groupoid. The reason is that how do we identify two sets? We give a bijection between them. And for that reason, there's a set of bijections between any two sets, so we get this definition of groupoid. And similarly, for vector spaces, there's a set of linear isomorphisms between two vector spaces. For smooth manifolds, there's a set of linear of diffeomorphisms between those two smooth manifolds. For schemes, etc., etc. So it's really important to understand that groupoids here is not an axiomatic definition in the same way as you might be used to. It's not a category where every morphism is an isomorphism. We'll come back to this later. A groupoid is a special kind of type. It's a type where there's a set many ways to identify any two elements. And so on, you can do this inductively, and you get this hierarchy of n types. So these actually do correspond to the homotopy n types. And if you don't know what that is, don't worry about it. It's not part of this talk. So one thing I want to mention is propositional truncation. So there's in fact truncation for any of these levels, but I'm just going to use propositional. So for any type, there is a proposition, which we call double bar, and we sometimes evocate this as merely x, and there's a map from x to merely x, which has this universal property. So for any map into a proposition, there's a unique map out of merely x. And so using this, we can actually define existential quantification, which is really nice. So I want to maybe point out, all I've done so far is given rules for building types out of new types. There's no logic in type theory. There's no logic of type theory, I should say. There's tons of logic in type theory. So here's how we define the existential quantifier in type theory. It's by taking the propositional truncation of the type of pairs. So the propositional truncation effectively identifies every two elements in your type. And so what we're saying here is that to prove that there exists an A of type A, such that B of A, it suffices to give a pair of an A and a thing in B of A. And remember, that thing might be an identification, so it might be like an equals, or it might be an equivalenceness. It might be a center of contraction, so it might be a proof that a type is contractible. It might be a proof that a function is an equivalence, which is a function that assigns a center of contraction to everything. So I want to note that a lot of these propositions are just types you write down. Propositions. But sometimes we don't want to keep around all the data. We want to say there is some data, but just don't keep it around. Like, for example, a manifold has an atlas, right? But the atlas is not part of the manifold. Having an atlas is part of the manifold. So this is what we see, is that we take the type of atlases and we take this propositional truncation. We're saying any two of them are good. We just need one. Any two of them are good. And that's how we make this this propositional truncation. So existential quantification is given by any pair. Any pair here will work. And similarly, we can get for all if B of A is a proposition for all A. Then the type of functions represents the proposition for all. And you can see that because to give a term of that type would be to prove that for all A, there's B of A holds. Because the proposition holds when it has some kind of term. Okay. Are there any questions about this? We're about to go to part 2.
So far, no questions have been asked. The time to ask is now if anybody is interested.
Yes. So it is going a little long. I apologize, everyone.
No, okay, no questions. It's just a comment. Someone saying there's nothing wrong with talking about elements of a type. The term just evokes syntax, and the intuition that type theory is about syntax has to die.
I wholeheartedly support that comment. That's really great.
Then it goes on and it says, in the same vein, set theory will soon disappear and element will naturally be used to describe the things that inhabit types.
I disagree with this. Set theory will exist because they're very useful kinds of types. Most of our math is set based, and will remain so. Maybe that's a discussion. We can have this flame war in the Zulu. Okay.
Sure. Please go on then.
I'm sorry?
And please go on. There are no other questions and comments.
Okay, great. So part 2 is category theory. So I don't have too much time to go over this, and I'm not going to get too deep into it. I just want to give a flavor of what it's like when you really take these ideas of type theory, that you have mathematical objects, everything is of a certain type, and what it means to identify them is based on what type of thing it is, and that you can figure that out just by what type of thing it is. You can figure out what it means to identify two things just by knowing what type of thing they are. When you take that into category theory, you get a lot of really nice features involving unique up to unique isomorphism. So, I have to give a definition here. So, in homotopy type theory, the notion of category fractures. So, there's a something which is called a pre-category, and that's what you think is a category, dear listener, unless if you're already one of the type theorists. A pre-category is to a category what a pre-order is to a partial order. So, a pre-category consists of a type of objects, and for any two objects, a set of morphisms. Remember, a set is just a certain kind of type. And it has composition functions and identity elements and all the usual identities between this. And I want to mention here that these identities here are equalities, right? Because we assume that you have a set of morphisms. So that's a nice feature. Once we assume we have a set of morphisms, asking for identifications between these is a proposition. So there's at most one way to do it. So we just ask the first one. Okay. So you can do all of category theory with pre-categories. It will work a lot like it does in the traditional foundations. You don't really gain anything. And there's a reason I like the term pre-category, which is to say, I like that I've put this sort of marker on the notion, saying it's not quite the whole thing, right? Is because you wouldn't want to do that, right? There's be no reason to do that. So we can do a little better. We can take the hot ideas seriously and look at what category theory would look like in a world where you actually natively have these identifications between things. So it's very common in category theory to say, and the obvious morphisms. So an obvious morphism is one whose definition can be derived, or that one can expect a community to reasonably derive from the definition of the objects of a category. So that's how I see the term being used in practice. And so we've seen that identifications are obvious in the sense that the obvious identifications, the one we know are native to the definition of a type, we actually calculated using the equivalence axiom and all these rules for identifications in homotopy type theory. So we would get the obvious isomorphisms, at least in a category, if the identifications between the objects were those isomorphisms. So this is our definition of a category. So a precategory is a category if it satisfies this extra proposition, namely that the function which takes an identification between objects to an isomorphism in that category defined in the usual way, isomorphism going this way and that way, and is an equivalence if this function is an equivalence. And we can define this function by setting reflexivity to the identity isomorphism. So that's how we actually get such a function in the first place. So what does this mean? A category is a precategory where the identifications between objects are precisely the isomorphisms. To identify objects is to give an isomorphism in that category. And therefore, that category has the obvious isomorphisms. You see very quickly that I had to shift there. I had to say obvious isomorphisms, not obvious morphisms. And there are sort of many attempts to bring that out in so-called directed type theories, the dream being that we could really say the obvious morphisms and mean it for everything. But for now, I'm just going to do isomorphisms. It still makes things work really nicely in category theory. So before you worry, there are a lot of categories. Most things you call categories already are categories in this sense and not just pre-categories. So for example, sets form a category, groups, abelian groups, vector spaces, models of behavior theory, they form a category. Topological spaces, smooth manifolds, schemes, etc., they form a category. Functors from any pre-category into a category are also form a category. And therefore, all pre-sheaf categories form a category, all sheaf purposes form a category, etc., etc. So most things. But I don't want to undersell pre-categories. They're actually very useful. They are what you might think of as presentations of categories. So a great example is one common category in you learn about in when you're learning category theory is the one object category whose isomorphisms are some group. So we usually write this as BG. That is a pre-category. It is not a category. The reason is it has a single object. So the self-identifications of that single object are there's just one, reflexivity. But obviously there's a lot of isomorphisms unless if it's the trivial group. Now there's an equivalent category, like actual category, namely the category of G torsors, where G is our group. There's a map from our pre-category to the category. It's in fact a universal map from that pre-category into a category. But it's still useful to have that category, right? You can think of it as a presentation with a little stricter notion on the objects. So they're useful. But you can always complete a pre-category into a category. It's called the rest completion. I'm not going to talk about that though. Okay. So universal properties are properties. What I mean by that is having a universal property is a proposition in the type theoretical notion. So as we saw before, being contractible or having a unique term, a unique element, is a proposition. And therefore, the type of terminal objects for a category is also a proposition. For any object, being terminal is a proposition. And moreover, since there's a unique isomorphism to between any two terminal objects, and since isomorphisms are identifications, there's a unique identification between two terminal objects. That means that having a terminal object, the type of terminal objects, I should say, the type of terminal objects is a proposition. Its identification types are contractible. So, so that the type of terminal objects can be seen as the proposition of having a terminal object. And since every universal property can be encoded as being terminal in some category, we see that the type of limits to any diagram is a proposition. And in general, take your favorite category, take its terminal object, that gives you a universal property for something. And so using that and using this theorem, which we can call categorical choice, we can avoid one of these weird choice appearances of choice that most people kind of ignore, which is how do you, so suppose you have a limit for every diagram, right? And you want to turn this into a functor. We never think about how to do this. It's obvious. You send every diagram to its limit, and then you send every morphism to the induced morphism on the limit, right? But what is its limit? You know there is a limit. You know they're unique up to unique isomorphism. But if you're trying to, if you have a set of objects and not a groupoid of objects, if you have a pre-category, then you have to pick one. Well, it turns out if you have an actual category, you don't have to pick one. And that comes from this theorem here, which you can call categorical choice. And it says this: if you have a fully faithful functor between categories, then for any object of the codomain, I'm sorry, that should say y of type obd, the type of pairs consisting of an object in the domain and an isomorphism of its image with your chosen object is a proposition. And because it's a proposition, remember the existential quantifier was this propositional truncation of the pair type. Because it's a proposition, the proposition that there exists an object there exists an essential preimage of y is equal to, is identified with this type of pairs. And what that means is that when you have a proof that there is such an object, you can actually extract one. Because you have a proof of there is an x such that f of x is isomorphic to y, you actually, by this lemma, and it's not a hard proof, it's a short proof, you have by this lemma an actual object and an actual isomorphism. And without any choice principles. So as a corollary of this, you get this nice theorem, which is true for categories and not in general true for pre-categories, that to identify two categories is the same as to give an equivalence between them, is the same as to give a essentially surjective, fully faithful functor from one to the other. And as you can see, being essentially surjective means there exists an essential preimage to every object, but because of the theorem up there, the categorical choice theorem, since the functor is fully faithful, we actually have one, and we have a witnessed isomorphism, so it's split, and that splitting gives us the inverse. This is a subtle point, but I'll talk about what exactly you'll use it for in just a few seconds. So, okay. So one of the upsides of this is you don't have to do with a choice of pullbacks, right? So I want to show here that you don't need global choice to take to make a limit functor. That takes every diagram to its limit, assuming that every diagram does admit a limit. And so the proof is very simple, right? We have a category of diagrams with a limit, and that's a full subcategory of diagrams. And by hypothesis, it's also essentially surjective. Right? So this is an equivalence by categorical choice, and there's no choice principle in that. It's just a theorem without even excluded middle, no non-constructive elements at all. We actually have the data. We have the data we need, so we can actually write down the specific element. Because it's an equivalence, we can go back along it. And so the composite of that inverse with the functor that just projects out the limit of that of the category of diagrams with a limit That's our desired limit functor. And so this is a little thing, right? It's a little quality of life thing. Maybe these things don't come up too much. After all, maybe we're happy assuming global choice. However, if you're trying to do things like, say, work with Lie categories, which are to categories what Lie groups are to groups, they have a manifold of objects and they have a manifold of morphisms and everything's smooth. Properties. If you have one of those, then choice fails, because choice is a strong discontinuity principle. And so one nice thing about this is by taking sort of one of these little places in mathematics, it's kind of annoying technical feature that most people like to ignore. Really focusing in on it and trying to really think about it carefully and using the actual notion of you can actually uniquely identify an object, you can actually get it. Taking that in your foundations, you can find something that's a very nice theory that generalizes later. So there are models of homotopy type theory in other settings other than set-based mathematics. So this is a meta talk right now. And one of these models, or actually many of these models, land in sort of topologically or algebraic, geometric, or smooth, diffeologically feeling spaces where types are actually stacks. And in this setting, you still have the right proof that essentially surjective, fully faithful functors are equivalences, even though choice is contradicted. So there is actually a nice theorem hiding here in what seems like maybe just a really deep dive into an extremely technical point. There's a lot of quality of life issues that come up when you use homotopy type theory to do category theory. It's hard to condense them very simply because the kinds of things that just happen when you're trying to do stuff, and the stuff you're trying to do is usually very, halfway through a proof of a theorem or of a lemma that's 3 lemmas deep, and everything's very particular. And it's just nice to know that every function you define is functorial on groupoids and things like this, as long as you've just defined it using the objects. So that's it. That's all I have. Thank you all very much. I'll take questions. I guess I'll also go after this. I'll probably go to the Zula and chat over there.
Thank you so much, David. That was actually a pretty nice talk. Very interesting to me. Okay, any questions? So there don't seem to be live questions right now. Okay, so in case you have any, please write on the Zulip's channel. The channel there will stay forever. So if you have questions next year, feel free. And we will upload a video to YouTube as soon as we have ready, so that in case anybody had connection glitches or somebody mentioned the stuttering problems, hopefully they're not going to be there. Okay. So for next week, we'll try to use YouTube again because it has a little buffer so we can avoid all the stuttering problems. I hope that by then the things will work. But we will use Zoom as a backup channel whenever YouTube fails, okay? So thank you all for coming, and, well, thanks to David again. See you all next week.